All right, so this is Unit 4, our first lesson on waves. So what we're going to do is we're going to go over the different parts of a wave, some properties of waves, such as reflections, and the different types of waves. So let's start with just a wave. So this is a wave. Right? It's something that repeats over and over and over again. It's very repetitive. And we're going to use a couple terms to help us with that later. But for now, let's look at the parts. Here we have our equilibrium line. This is sort of the center of the wave. And the wave will either go above that or below that in what we call a crest up above and a trough down below. So again, crest, trough, crest, and just repeating. Right? Trough, crest, trough, and so on. Now the distance between that center equilibrium and your crest is the amplitude, which is the exact same as the distance between that center equilibrium and your trough. So this distance, or this distance, or this distance, whatever you want, from the center to either your maximum point to your minimum point, we call the amplitude. Now I said it repeats, right? So for example, let's say we start at the crest, we go down and back up, like this, and then we repeat, right? And we go down and back up, and then we repeat again, down and back up, and so on. Now that horizontal distance, right, from one point to the next point where we repeat, that distance we call a wavelength. Now wavelength you don't necessarily have to measure from crest to crest. You could measure from trough to trough. That length is also a wavelength. And the symbol for wavelength we write as the Greek symbol lambda, which looks like that. That means wavelength. All right. Next, I want to talk about phase. So a phase is when you have a point on the wave that is in the same position as another point and doing the same thing. Right, so let me look at a couple points here. If we were to look at this crest and that crest, those 2 points are in phase. They're the exact same point on the wave. Same with this point and this point. Right, but we can also say this point and that point are in phase. However, is the tricky bit. Although these 2 blue points are in phase, they are not in phase with the green points. And this is why. I want you to try and imagine this. So we have the wave moving in this direction. Now as it moves in this direction, this point is going to fall, and this point will fall. But the green point will rise as this crest approaches it. This trough will approach the blue point, this trough will approach that blue point. So not only are they in the same position, they are doing the same thing. But this green point, not in the same position, it's going to move up. So they are out of phase. All right, so next are the 2 types of waves. We have a transverse wave and a longitudinal wave. Now a transverse wave is when the particles are going to move perpendicular to the direction that the wave moves. Right? Like that. That's a transverse wave. A longitudinal wave is where the particles are going to move parallel to the direction of the wave. So that would look like this. Okay. So next thing I want to go over is wave reflections. Right, so here, this is just a simulation, but in this simulation, I can make a pulse over here that sends a wave, and then it's going to reflect off of this point and bounce back. Now this is a fixed point, meaning it's not going to move. We have a C-clamp right on there. It's not going anywhere. So watch what happens when it reflects. Notice that it reflects on the opposite side. So it gets inverted and comes back on the opposite side. I'll show you again. Okay. Now, if I make it a loose end or a free end, so that this is just a pole with a ring on it that can move up and down, watch what happens to the reflection. So when it's a free end reflection, it does not get inverted. Notice that this end simulates a fixed end reflection, and it does get inverted. So that's the two differences between fixed and free end. Free end, no inversion. Fixed end, inversion. Two other new terms I want to go over. So this is our transverse wave. You can see the direction of the wave is to the right in this example, right? Moving this way. But the particles are moving perpendicular to that. Now with the slinky example that I showed you, it was you had the direction moving this way and any point moving back and forth, parallel to the direction. Now on a transverse wave, we had a crest and a trough, but we don't have that. We don't have a maximum point and a minimum point on a longitudinal wave. What we have is a point or points where that wave gets more compressed. So we call this an area of compression. And then the opposite, we call an area of rarefaction. Not refraction, it's not grade 10 optics, even though the words sound the same, rarefaction. Okay? So the first problem is going to have us introduce some new variables, two new variables, period and frequency. So I said that this wave is very repetitive. In fact, if I just had a wave moving on its own, you wouldn't be able to tell where it started and where it finished. And I can actually show you. Alright, so here we have a wave. Again, it looks a little weird in the video if you're going back to watch this video later. Right? You're not going to see it the way we see it here because the video takes certain pictures every second, and this is on a certain frequency to vibrate. But you can't really tell where it starts either way. But you can tell it's repeating. And it's repeating a certain amount of times every second. Because of that, we have two terms that we use here. One is called period, and that's in a certain amount of time divided by how many times it repeats itself. Now, frequency is the exact inverse of that. That's how many times does it repeat every second. So the number of cycles doesn't have a unit, so period is measured in seconds, and frequency is measured in per second. But we don't actually call it per second, we call it hertz. And this you might, recall if you want to listen to your favorite radio station. It's in a certain hertz or kilohertz or megahertz. Right? It's because the frequency, the electromagnetic waves that are being sent, you have to tune into it at the same frequency to actually listen on the radio. Right? This I currently have to 22 hertz. So our wave here is moving at 22 hertz. I'm not sure about the specifications of the camera, but if I can get their frequencies to match, it'll look like the wave is completely still. Okay, and I'm going to show you another cool video about that as well. But first, let's try the first problem. So you're at a beach and you're watching the waves hit the shore, one after the other. And you decide, I'm going to time how long it takes between two successive waves. So one wave hits, you start the timer, you wait, the next wave comes. When it hits, you stop the timer and you measure 3.5 seconds. You're wondering, okay, what's the period and frequency? Well, the period is time over cycles. So you got 3.5 seconds, okay, and you only measured one cycle from one crest to the next crest. So over 1. So our period is 3.5 seconds. Now your frequency is the exact inverse of that. Now you can do 1 over 3.5 like this equation, or you just do 1 over period. Same thing. So 1 over 3.5 seconds, which gives you a frequency of 0.29 hertz. Second question says you generate a series of waves in an 8.5 meter long clothesline. Okay, similar to this, if you want to imagine this. It's not 8.5 meters, but let's imagine it to be. By jiggling one end of the clothesline up and down rapidly, just like we do with that frequency generator at the end there. You notice that the wave crests are about 0.5 meters apart, and that the first pulse returns to your hand 2.5 seconds after you start moving the clothesline. Find the frequency, wavelength, and speed. Okay, so let's draw what this looks like. So here's our clothesline, and then we draw these pulses and we get a wave, something like this. Right, where the entire thing is 8.5 meters long. Right. I should have more crests there because it says, you notice that the wave crests are 0.5 meters apart. So from this crest to the next crest, it says it's 0.5 meters. So yeah, I should have a lot more crests for that to add up to 8.5. But let's not worry about that. This is not to scale or anything like that. It's just a visual to help us. So I mean, the first question says, what's the, well, not the first one, but the wavelength we can figure out already. Right? Because it tells us crest to crest is 0.5 meters. So the wavelength, therefore, is 0.5 meters. It's already in the question for us. We just had to identify it. And this says the first pulse returns to your hand 2.5 seconds after you start moving the clothesline. Okay, well, if it goes from here over here, let's just follow the first pulse, and then comes all the way back to your hand after 2.5 seconds, well, we can calculate the speed of that wave. Right? The speed of that wave would be the total distance, which is 8.5 times 2, so 2 times 8.5, right, divided by the time, which is 2.5 seconds. That's meters. We get 6.8 meters per second. But I want to show you something else. But first, let's figure out the frequency. Now, the frequency, right, from our previous equation is the number of cycles per time. Okay. Now, if you were to look at all of these crests, right? And you can count them all, right? You would count a total of 17 cycles, right? And going all the way there and coming all the way back, so that's twice as much, in a time of 2.5 seconds. Which gives you a frequency of 13.6 hertz. Now, there is another way to calculate the speed of a wave. Right? So another way to calculate the speed of the wave is to look carefully at the wavelength and the frequency. So actually, I'm going to turn this thing back on. Okay, so the wavelength, we can look, say, this crest to this crest. That's the wavelength. Okay, if you want, you can grab a meter stick. I don't know what happened to mine. And you can actually measure that wavelength. Now this is going pretty fast, but if you were to measure it and count it, right? Maybe looked at this and pretty much as it's going up and down, counted how many times it smacks into my hand as it comes up, right? And time it over a certain time, then I can figure out the frequency. Now in this case, it tells me the frequency. It's, well, very specifically 21.78 hertz. Now to figure out the velocity, well, if you imagine one wave starting here and moving here, it travels a certain wavelength within that frequency, right? Or distance, if you remember, is velocity times time. So velocity is distance divided by time. In this case, it would be velocity is the distance. I'm going to write distance over time. But if our distance is simply one wavelength, it's also the wavelength divided by the period. Because remember what the period is? The period is defined as the time it takes for one cycle. So the time it takes for one crest to go from here to here, which is perfect. And I can rearrange that. Knowing that frequency is 1 over period, I can write the speed of the wave is frequency times wavelength. And this is the F equals ma of this unit for waves. This is called the universal wave equation. And it tells you that the speed of the wave is equal to its frequency times the wavelength. And we can even confirm that right here. Right? We calculated the velocity or speed this way, right, using distance over time, but we could also figure it out by taking the wavelength, speed equals the wavelength, which is 0.5 meters, times the frequency, which is 13.6 hertz. And if you do that on your calculator, you'll get exactly what we got before, 6.8 meters per second. So there was a couple of ways you could have done this question. Okay, you could have figured out, well, the wavelength is given. Then you could have found velocity like this. And then if you wanted to, you didn't have to find frequency like this. You could have used the universal wave equation, knowing velocity and wavelength, and solve for frequency.